Good morning. Good morning. Today we have a very interesting conference by Jorge Ballesteros. The title is Transforming the Energy Future for Application of Artificial Intelligence and Big Data in Infrastructure Operation at ITER. Well, ITER is el Instituto Tecnológico de Energías Renovables, ¿no? En Tenerife. So, about Jorge Ballesteros, he has a master's degree in telecommunication engineering with experience in research projects in robotics, artificial intelligence, and data visualization and simulation. He currently works as head of the robotic unit at the ITER, applying robotic solutions in the field of renewable energy. He's also a member of the advisory board of Caja 7, chair in Big Data, Open Data, and Blockchain at the University of La Laguna. So I think you can proceed, Jorge.
Okay, thank you very much. It's okay? It's okay? Okay, I think it's working. Okay, so, well, thank you very much for your invitation to this Congress. We are pleased to be here. We at ITER, I'm gonna start with an introduction of what is ITER for the people who doesn't know still who is ITER, and that it may be a lot of people. And then we are going to focus on what we do at Robotics and Automation Unit at ITER, focus on renewable energy. For those that you don't know, ITER is a technological institute. It's a research and development center located in Granadilla, Dabona, Tenerife, south of Tenerife. And right now, or nowadays, it represents the main institution of research, of public research, along with the University of La Laguna in Tenerife in terms of renewable energy. We are 180 people working there, and we started mostly with renewable energies. Our core is renewable energy, but we have been expanded through the last 10 years to another fields or areas. And right now, we not only work on wind or PV energy or storage, but we also have several lines of activity in ICT, sustainable architecture, genomics, and environmental sciences. And one of the last ones that have been started is robotics, that we started at 2018. Okay, so as I said, our core is renewable energy production. We manage over 40 megawatts of solar power and 60 megawatts of wind power energy. And we do the operation and management of those resources. At the same time, we have a very unique smart grid at the facilities of Granadilla side, because we have lots of different type of consumption, production, and storage units. So it's a very good place to validate technology in there, because we have low-level control of everything. I mean, for example, we do not use, we produce our own inverters, solar inverters. We have very low control of everything, up to the electrical signals. And also, in the last 10 years, we have opened a service that is focused on HPC and cloud computing, that we have a supercomputer located in there that probably in the following 2 years we're going to expand to another one. And it's very useful for us at robotics because we need lots of computing power. So, well, this is one of the main new wind parks that we have installed, three of them in 2018, and 3 of them were before that and are at the end of their life, 25 years power, 35 years of production of wind energy. It was the first wind energy park installed in Tenerife. And right now we are working on repowering, doing the whole reinstallation of all the wind turbines on those three parks. Also, we have deployed 40 megawatts of solar power. Those that are showing there is in the Granadilla side. These are offices below there and storage sites. And also, this is really beautiful. It's the bioclimate house residential area that is also located in Granadilla side, and it's also a living lab that is completely equipped with lots of sensors to measure information about the conditions of the people staying there. And well, as I said, it's 2018 right now. ITER decided to create a robotics unit, and I was chosen to be the leader of that unit. It's focused on robotics and automation. We started with what people normally think about robotics is physical robots. Okay, we started doing that at the very beginning, but as the time has gone by, we have oriented to go to the application of artificial intelligence, because it's what is more applicable to renewable energies right now, and is what the market and all the requirements of the business or the entity was focused on. So we are these people here. I am representing them. And Richard is one of the people. Richard and Carlos Eguona are also working with University of La Laguna in some articles and papers we're preparing. We focus on data. Everything we do is about data right now, and we use different types of equipments to gather data. That is mostly through drones or through metering sensors, and we produce lots of data, normally called big data, and then we use artificial intelligence to exploit that data. This is the 4 pivotal technologies that we use at the robotics unit. So we are year 2020. COVID has just passed, everything is a mess, and we have to look ourselves. That little stop was very useful for us, because we were doing things for a lot of years in a way that time, that period that we could think a little bit of what we were doing, let us know that we were not doing the properly way. So we have no management of data, we have no policies, we have no maintenance of the service related to data, and that led to chaos, complete chaos. It was impossible. We have more than 150 databases with lots of different types of data, different technologies, different manners or different ways to access to this data. All were delocated. Some of them were abandoned because nobody used that data. The ones that were not abandoned, nobody was taking care of that data. So we had to stop and say, okay, we need to focus, we need to centralize all that, we need to provide with a central point where all the data of the field devices is gathered, and then that data will be accessible in the same way for everything. It doesn't matter if it's an inverter, it's a wind turbine, it's a meteorological station, is a water meter, it doesn't matter. Everything goes in the same way, and everything is queried in the same way. And it took a lot of time, first to gather all the information that we were previously gathering, trying to decipher how was getting that information from, and then building a system that it was scalable, it was reliable, and it could grow without having fear, okay? Because as the things grows, in terms of big data, there are some fears because you need lots of resources, and it's difficult to analyze something that is not right now. It's going to be in 5 or 10 years, and how to measure that is difficult. So we focus on working on open source software and doing all ourselves. Because if we go to providers, license fees will be impossible to accept. So going back of what we right now have 44.3 megawatts of wind power installed, 65 of solar, and 1.5 megawatts hour battery storage of energy. Also, we have our own self-managed stations, meteo stations, and another 90 stations that we gather from different APIs or services provided mostly from GrafCan and Cabildo de Tenerife, that they provide open data on meteo stations. Then we have more than 10 water meters distributed along the Granadilla side to control distribution of our own water production. And also 25 bioclimatic homes where we gather water, energy, and also environmental sensors. And well, this is a picture from the above, from the Granadilla side. So I have just spoken about the production and the bioclimatic buildings. But here right now you have lots and other buildings. We have industrial buildings, we have office buildings right here. We have 25 different points of consumption with different profiles. So we have a very rich validation site for all that matters in terms of power. What we faced was we had very different devices. EV chargers, energy meters, different gateways, different network analyzers, meteo stations, water meters, any type of sensor, of environmental sensor you can think of. It was completely very difficult to gather all that information and to speak to all these devices with different protocols. But for us, the work was trying to connect with them. I mean, once we connect with the device, everything will be clean, everything will be transparent, and we will transfer the information in the same way to the system. Information and data will be stored, and that information will be available with the same endpoint, with the same interface, independently from what the device is. So you can imagine what we had in mind at that time, more than 1,500 devices that we have to put all together in one place. So what we decided to do? Well, we started what was a project on that time, now it's become a service of the business, of the entity, where we have to do all the data acquisition, monitoring, and visualization of data. Is what we call right now Nexo, and well, there is a list there of all the things that we gather information from. Okay, so right now, as I said, more than 1,040 devices, more than 65,000 variables, and it's generating nearly 10 million messages an hour. It's a massive amount of data. These are the 4 pillars that we focus on when we are speaking about data. Well, first of all is visualization. We work mostly on developing dashboards and doing data fusion from different inputs, and also orienting it to data comparison. Also, we do monitoring, events and anomalies on data, issues that are related to data, and then deliver those incidents or those issues to operation and maintenance department. Then, in terms of business, we work more on metrics and calculating metrics, calculating trends, and providing with business intelligence to the direction of the institute. And most of it, we do it through exploitation of the data. And mostly we work on forecasting, doing automations, and using, most of the time, artificial intelligence. Most of the time, in this case, is about machine learning right now. But I'm going to speak later on other new technologies within artificial intelligence that we are using. So I'm going to give you here, I'm going to be a little bit fast because there is lots of things to show, but I'm going to go through different visualizations that we have developed. Here, for example, is a dashboard of the wind power generation that is the main screen for the wind energy department. In one view, they can see latest production of the last day, status of the data, incidents, location, distribution in one single panel. We can do that with very low dedication because we have a platform that is nearly no code. We use different user-friendly instruments to perform these visualizations. And then we go from high level in terms of plant to low level in terms of, in this example, for example, into the wind turbine. So we got a view of the whole plant and then going further or going deeper in the analysis and going up to the wind turbine. This wind turbine information is gathered through another external SCADA. For example, on photovoltaics, we have the same view as you viewed before in wind energy, that we see all the distribution, all the location of the park, all the incidents or issues, production of the last day, of the latest week, and also real-time resource availability and production. Then if we go inside one of the plants, we can see meters, we can see rooms, as we call casetas, is where we storage the inverters. We can see the status and the production of every inverter. And we can see 3 days power production. And well, it's very interesting because we see at the same time the resource, the production, the estimation of production, ideal production, and also the limitation that the energy operator provides us. Here in Canary Island, we have a very big problem on power limitations right now. Right now we are about 17 to 20% limitation of power. And this is a big issue for power producers, as ITER is. In case of the PV, we also can see internal information of the inverter because we produce our own inverters. We manufacture our own inverters, so we have low-level access to every electrical data. And I'm going to focus on this one because it is very related to some work that University of La Laguna is doing, that this is the production time series of an inverter, but at the same time we see the resource that is in yellow, and we have been working in the last 3 months in performing PR calculation on a minute basis. That it is normally made on a daily basis, we are doing it on daily basis, on minute basis. And this information is becoming very interesting for us because we do not have to wait until the next day to know if the inverter is having a good performance, independently from the solar irradiance. We can know that in real time. And we are gathering very good results, and that methodology, maybe we're going to work on publishing one paper on that. Well, as you can see here is, well, the other signals are the limitations and production. As I say, the green one is the PR. Also, we gather information from weather stations. We have here a comparison of all the weather stations that we manage. So we can, in one view, all those charts that you see there are expandable, so we can see it in full screen. And we can compare the wind resource or the solar irradiance resource in every site that we have a plant or a park. Also, we get data from outside. I mean, we get data from the operator. We get data from open data from the operator, so we can simultaneously see what we are producing and what the energy demands. What the energy demands, and also what the energy distribution of energy is producing right now. So it's very important for us to know what's happening there outside, to know if we are going, for example, to receive any limitation. That is really useful. And we support that analysis on open data provided by Red Eléctrica de España. This is another panel that is mostly for dissemination purposes, but it shows our production during the last year, during the last month, distributed by technology, by plant, and also with some indicators that we are producing. And there is one big indicator here that we are producing right now 28%, between 25 and 30% of the energy produced in Tenerife is produced by ITER. Renewable energy. Not the whole energy. The rest of the energy is not produced by. But in terms of renewable energy, nearly 29% is produced by ITER or managed by ITER. This is a screen that tries to show the amount of data that we are handling right now. And as I said before, we have lots of data. Normally we are about 8 million messages per hour, and sometimes of the day we have peaks like that because we receive lots of data in specific times. But it's manageable. Our system can accept 25 million messages in just 1 hour. And it could accept much more than that, because thanks that we have our own HPC infrastructure, we can escalate. Now I'm going to focus on the data exploitation, okay? Delphos is a project about forecasting of all the energy-related time series. Red Eléctrica de España imposes that any energy provider with an installation of more than 1 megawatt has to provide with 48 forecasting production of that installation. So right now we are generating on a daily basis 70 1-hour forecast of wind and solar energy production. And you can see in the dashboard, well, here is all mixed because we need to do this visualization. Here you see the real power. Here is forecasted power, and this one is using different models. There are different models that we use, different machine learning models, and we on a weekly basis we compare all of them. We compare the results and we balance the use of them. So it's not all the time using the same model. We combine them. And this view is very interesting because we can see what we suspected that we are going to produce today, what is going to be expected to produce during this week, and what is going to be expected in real time, okay? And then we have also an analysis here on the difference that we had on what we said we were going to produce and what was produced. Sometimes there are some difference because we cannot perfectly forecast. For example, because the forecast is 1 hour forecast, okay? It's hourly forecast. And sometimes you cannot forecast when it's going to be cloudy. Maybe we have success, but we have a delay of 2 hours when the cloud appears. But Red Eléctrica de España doesn't matter about that. I mean, we have to do it in an hourly basis. And this is a big issue because the biggest difference is with the forecast, you got penalized, economically penalized. So if the forecast is very big, is the difference in the forecast is very big, you got penalization. And that penalty is becoming an issue. It's quite a lot. Here you can see in detail, and this is the limitation. The forecast is the purple one, and the production is the green one. So in terms of solar, we are doing a very good work. The only, in this graph, for example, this is a week. The only day that we had big difference was due to a limitation, not due to a forecasting problem. So this area right here, we don't get penalized, okay, because it's an external limitation. What we get penalized is for this type of things. But this, for example, may be a 3-hour cloud that we didn't expect to appear. I mean, the difference is very slow. It's very small, but it's important. And also, we do forecasting on consumption. This is also very, very nice because we can know in 40 hours in advance or estimate if we are going to have lots of consumption. And our profile of consumption is more relating to production of air conditioners, because most of our facilities are bioclimatic, but some of them are not. So we need air condition on summer days mostly. But here we have a combined forecast of all the data points or consumption points in the area. Another thing that we also do in robotics and automation units is aerial inspection of wind and photovoltaic energy infrastructure. We use drones to get data, not in terms of time series, but in terms in image, and using mostly thermal imaging. We use this type of drones. We do periodical flights through the whole installation of PV plants. Flying one PV plant, it takes about 15 minutes. We need to fly around 450 PV plants during the whole year. It's quite an issue because there are lots and there are distance between them. So we repeat every flight every 2 years. We cannot do more than that with 4 people doing that. But well, as you can see here, what you can see below in here is reconstruction of all the images that we get. And here is the GraphCam map that is very good resolution. But you can see here what resolution that we have right now is this one. And I can go and I can see up to a cell. Very, very, very detailed. And also, we get thermal imaging that in this case is showing us that that zone of the plant is dirty. Because radiation, when the solar radiation impacts the surface, is different. The radiance, the irradiation of the panel is different when it's dirty than when it's not, when it's clean. And we are working in a project that I'm going to speak later that is focused on this issue. We have lots of problems with with PV cleaning in Tenerife because we are in a very, very critical place that is plenty of wind, very close to the sea, with lots of salitre, that is concentration of salt, and that mixed with dust is the worst things for PV. Well, we also do the same approach, but we do it on wind turbines, and we gather thermal and RGB imaging of the wind turbines. And there are some studies, and we are also applying it, that in some cases you cannot see, for example, breaks in the fiber. Visually you cannot see it, but if you get the thermal imaging and there is enough heat on the surface of the forgot the name in English, well, of this area, okay, the blade, okay, on the surface of the blade you can see the break. You can see a break in there, even if it's not visible. And we are using it to get in advance to a replacement or to a fix to that blade. This is what we are very happy right now to be working, and I think it's going to be impactful for you. We are applying right now Gen AI. I mean, ChatGPT is the daily basis for most of us. I don't know if it's for you, but for us it's the daily basis using GPTs. Well, we have developed our own GPT, our own ChatGPT in the business, in the entity, using the same technologies that they use, but supported not on ChatGPT, on OpenAI or Claude models, but on open models, okay? So we deploy those models on our HPC computing site, and we configure and we provide with internal information of the entity in terms of production, billing, economic or even organizational data. I'm going to focus here on energy-related things, okay? So for example, we have a screen like that. You see, it's nearly ChatGPT-like. And we say, okay, give me the product. I had no time to translate this because I speak with the GPT, I speak in Spanish, okay? But this is what I ask to the system. And I say, okay, dame la producción. Give me the production, energy production of the last 7 days in the Finca Verde, that is an installation that we manage, meter, okay? And the result is this. We have two models that in one model it provides with data, and in the other model it provides with visualization, okay? And it says, okay, choosing devices and variables, constructing the query, this is the start date, this is the end date, this is the interval, and then it generates an URL, okay? And in this side, is just analyzing all the dashboards that we have, that are more than 70 dashboards, and the assistant knows which is the dashboard I am interested, and it directs to the dashboard, to the next dashboard. And the result of the first one, that I think is the most interesting, automatically queries the database, returns with a data set of what we ask in natural language. So we can get now this data set, and we can download it, we can analyze it, and we can also share it with anyone. So, for example, when Benjamin and his people, Javier and Silvia, ask for a data set, for me it does not take more than 1 minute to build that data set. And 3 years ago, it may take hours to build that data set, okay? Another thing, another interesting thing, this is another assistant we have developed that provides or generates reports. Does not provide data, it generates reports. So for example, in this case, I asked total production of the last month for every meter. Shows the maximum, the date on the maximum value and on the minimum value and the number of records. And this is the answer. The answer is, okay, I'm going to provide with a useful report. The objective is to get the production of the last month per meter, and then it shows how it's going to build the report, how it's going to build the queries to the databases. It shows us the results of the queries that have automatically created, and then at the very end, automatically generates a report of energy production per meter of the last month. And well, it's very long. I'm just going to give you a sneak peek. This is just the introduction. It's 10 pages report. And well, I wanted just to show you that we have just asked the second sentence. Total production of the last week per meter. This is the only thing that we provide with to the system. And the system answers with a 10-page report with 100% precision. And it does, I mean, it's very good because there is no human interaction in here. So these kind of systems, when interact with numbers, are very good. And also conclusions are not bad, but we can get that report. We are not okay with something that the report is, well, okay, we can import it, we can download as a doc, and we can edit it. But we do not have to build, for example, a monthly report of every installation from zero. So that gives us peace. Peace. You remember we were in chaos. Right now we are in peace. Not total peace because there are lots of things, but we are now, in terms of data, we are in peace. Now I'm going to go through the research projects that we are working right now. I'm going to be fast. We are opening a line on ports. There is a big issue on energy production on ports and energy requirements. There is a law that by 2030, all the energy that the ports provide to the ships needs to be renewable energy. That is going to be impossible. It's impossible because, for example, every cruise ship that, for example, enters the port of Tenerife, when they plug into the energy system is 2 megawatts. It's impossible to deploy this kind of massive needs of renewable energy installed in a period of 5 years in all the ports of Europe. It's impossible. But there is a regulation that imposes that. So the ports right now are running trying to accomplish that regulation that is, as I said, for me it's going to be impossible, but that they will try to reach as much as they can. And right now we are working with in a pilot project with 5 ports along Europe in trying to analyze all the regulations per country that are different in most cases. And also trying to provide with insight on how to deploy all that renewable energy installations that they need, and also to provide with a digitalization of that infrastructure so they can know what they are producing or what they are consuming and gathering, well, just something like we did 5 years ago in ITER, ports are going to do it right now. Another project is so-called about aerogenia, is related to that I spoke to you before about wind turbine aerial inspection, and also combine that data with electrical data, working with Universidad Politécnica de Madrid, Universidad de Alcalá, SIROCO. SIROCO is a project that sounds really close to what is working in University of La Laguna. And we are working on, as I said, a predictive system for the presence of environmental waste or dust and corrosion in both using electrical information and also image. Voltaire. Voltaire is our best hope on research terms. We are going to build a digital twin of our whole system. Just one small data. We consume nearly 1 megawatt per hour at ITER. We have a very big consumption site and also a very big generation site, so it's a big self-consumption site. And we are going to focus or trying to get knowledge through this project on how are we going to implement that self-consumption system. What's next? Another thing that is very interesting here is to know when we are going to get a set point or a limitation in the future for the operation of the energy infrastructure. I mean, if you know when the system is going to say to you, you can only produce 50%, it's very useful to know that information in advance, because you can do whatever you want with that energy. Instead of right now, we are losing it. We are then throwing to the bin. If we know we will not be producing the 50% we can in wind energy tomorrow, we can divert that energy, for example, to a storage system, or we can plan to stop to do a maintenance operation on the wind turbine, for example. This is a very nice. We have been 6 months since we are testing models of forecasting, and we have some nice results, but we need more testing. Also, autonomous operation of our self-consumption site. This is related to the Voltaire project. Okay, this is a profile of our consumption. As you see here, is nearly 750 kilowatts, and this is the day that we have production of solar energy. But we can analyze removing and adding different points of consumption and generation, and it's very nice to see that as an historical, because we can really understand when we are what we need to be sustainable, to be completely sustainable, that we are not right now. Sorry. And then the last two things that we want to speak is about a hybrid PV plant that is going to be installed just before the 30th of December of this year in Arico. It's a 50 megawatts photovoltaic plant, 50 megawatts hour battery storage. It's going to be the first one installed in Tenerife in hybrid technology. And the last is maybe a big project, but is agro-PV plant that we are working with Cabildo de Tenerife to install a 200 kilowatt peak plant in vineyards in the area of Tegueste. Okay, so that's all. Thank you for your attention.
Well, thank you, Jorge. Very interesting. One question or two?
Okay.
Well, I have a question for you. What you say that you can use artificial intelligence for balancing the system. Mm-hmm. And here at this conference, we had quite a lot of papers on designing an energy management system based on, let's call them, classical methods, or analytical methods like optimization. How superior artificial intelligence to optimization for balancing a system?
I mean, in terms of artificial intelligence is the broadest way to call very different types of techniques. Classical methods are mostly focused on statistical methods that in terms of the last 10 years have evolved to, for example, machine learning or regression, lots of typical things that people were doing lots of years ago. In the last 3 years, there is a boom of generative or Gen AI, that is what supports GPTs. And nowadays, everything is focusing onto that, because the programmer or the technician does not need to know extensive mathematical knowledge. It just speaks with a model. Right now, I could say that generative AI, it cannot beat very fine-tuned machine learning models. But I think in the next 6 months or maybe 1 year, that models could be up to the classical or machine learning models in terms of forecasting, analyzing, are going to be very, very good. Right now, the trend is going very, very high. It's going on a big steep. I'm not an oracle, but as what I see is that in 1 year, maybe generative AI models will do most of the things that right now are doing it with classical models or machine learning models.
Good. So probably in the next conference, after next one, we will see some research work based on artificial intelligence instead. Thank you very much.
Okay, thank you.
Okay, hello to everyone. Let's begin with the last session of this conference. I think the number is E. Okay, it's the same. Next presentation is about the influence of synchronous condenser on a small isolated power system with large amount of renewable energy. A case study of the Lanzarote-Fuerteventura power system is presented by Mr. Medina Dominguez.
Thank you, Mr. Francisco Javier. Good morning, everyone. As Mr. Francisco Javier said, I'm Elías Jesús Medina Dominguez. I am a PhD electrical engineer, project technician in the Canary Islands Institute of Technology in its renewable energy department. I present our research work called The Influence of Synchronous Condenser on a Small Isolated Power System with a Large Amount of Renewable Energy, a case study of Lanzarote-Fuerteventura power system. First of all, in this presentation, we will see a short introduction of this work, its purpose, and a brief description of the synchronous condensers and Lanzarote-Fuerteventura electric power system. After that methodology, it will be presented. Next, we could see the results. And finally, I present the conclusions and possible next steps. The purpose of this work is the analysis of effects of synchronous condensers on a small isolated power system with large amount of wind power. In this case, the small isolated power system is based on diesel generation. The analysis considers different values of inertia constant of the synchronous condenser. This is a technical analysis based on the transient stability and voltage stability. As I said, the Lanzarote-Fuerteventura electric power system is used as a good real example of a small isolated power system. The synchronous condenser, also known as synchronous compensator, synchronous capacitor, or SYNCON, is basically a synchronous machine connected to the grid without prime mover or mechanical load. Synchronous condenser has been used in power system from 1930. However, they have gained importance in recent years due to their capabilities that favor the integration of renewable energy into the electric power system. Some of those capabilities are generation or consumption of reactive power to help the voltage control in the power system, the inertial response. They can provide the inertia to the power system, as well they can contribute to the short circuit capacity. Lanzarote-Fuerteventura electric power system is located on Spanish islands of Lanzarote and Fuerteventura. The power system on Lanzarote Island is connected to that in Fuerteventura Island by two submarine power cables. There are basically two rated voltage in transmission level, 66 kilovolts and 132 kilovolts. Both islands have a conventional power plant based on diesel generation units and gas turbine generation units. The total conventional power installed is 541 megawatts. The total wind power in the power system is around 97 megawatts. The methodology. Methodology relies on transient stability and voltage stability analysis of two synchronous condensers to the electric power system. So, the modeling of Lanzarote-Fuerteventura power system and the synchronous condensers, as well as the performance of the simulations, were carried out using PSSE software. The considering disturbance in the power system for analysis is a sudden disconnection of a conventional generation unit belonging to the conventional power plant on Lanzarote. The effects are assessed by the rate of change of frequency nadir, and minimum voltage. The two synchronous condensers are connected to the Lanzarote power system, as you can see on the right side of the slide. One of them is connected to the power system on Lanzarote Island, and the other one is connected in Fuerteventura Island. Synchronous condensers are Cellian pole synchronous machines with a rated apparent power of 25 MVA. So, synchronous condenser can inject or consume reactive power up to this value. A range of inertia constant of the synchronous condenser is considered from 2 seconds up to 7 seconds. The system states of the power system for analysis is the strain power demand conditions in normal operation. They are annual peak demand state and annual peak demand state. So, given the above, 3 cases were studied. The first one is called conventional case. All of the power demand is covered by the conventional generation. The second case is the conventional wind case. The 30% of the power is generated by the wind generation, and the rest is produced by the conventional generation. The last case is called conventional wind synchronous case. The power demand coverage is the same as the previous case, but synchronous condensers are connected with their different inertia constant values. The result. It's on the slide, the system frequency time evolution when the disconnection of the conventional generation takes place. First of all, we can see the expected system frequency drop. After all, the power system can remain the stability and new steady state is reached. Result also show higher rate of change of frequency values and lower frequency nadir values in conventional wind case. The reason is that in conventional wind case, there are fewer conventional generation units connected. It brings a lower total inertial response and a lower total active power frequency control. Now we can compare the system frequency time evolution for synchronous condenser case. The results show lowest rate of change of frequency for synchronous condenser case and higher frequency nadir for synchronous condenser case than the conventional wind case. On the other hand, it's also observed a certain delay in the system frequency recovery when the synchronous condenser is connected compared to the conventional wind case. This system frequency behavior is due to the inertial response of the synchronous condenser. When the conventional unit disconnects, the synchronous condensers inject active power to the grid from their rotational kinetic energy. After that, the synchronous condenser consumes active power from the grid in order to restore their rotational kinetic energy. The result of the range of the inertia constant value of the synchronous condenser suggests lower rate of change of frequency values and higher frequency nadir values when inertia constant of the synchronous condenser is increased. Besides, the system frequency recovery, the delay is more noticeable. The reason is as higher inertia constant of the synchronous condenser means higher rotational kinetic energy, the inertial response of the synchronous condenser is also higher, and this produces those results. It should be noted that the relationship between rate of change of frequency and frequency nadir with the inertia constant are not a linear relation. It suggests, this is not the linear relationship, suggests the existence of a technical economic limit for inertia constant of the synchronous condensers. With regard to the voltage time evolution for some transmission bus bar are presented for both conventional case and conventional wind case. When this conventional generation disconnects, a voltage drop appears throughout the small isolated power system. After that, the voltage recovers. Voltage drop is deeper in conventional wind case. The reason is that in conventional wind case, there are a fewer conventional generation units connected to the grid. So it brings a lower reactive power control. The voltage drop is less severe when the synchronous condenser is connected to the grid. Synchronous condenser can provide their reactive power control to the power system. So when the conventional generation disconnects, the synchronous condenser increases the reactive power to support the voltage in the power system, and it causes the smaller voltage drop in the power system. Result also indicates that the different inertia constant values considered did not have significantly different effects on the voltage of the power system. The conclusions. The findings indicates that the synchronous condenser caused a reduction in the rate of change of frequency values, as well as cause a higher frequency in either values. Therefore, a reduction in the system frequency excursion can be expected when a disturbance takes place in the power system. A certain delay in the system frequency recovery is also observed. So we must take into account this delay because it may lead to a significant negative impact on the power system. Synchronous condensers result in less severe voltage drop throughout the small isolated power system, and the findings also indicate the existence of a technical, economical, optimal value of the inertia constant of the synchronous condenser. Based in the positive findings, we can affirm that the synchronous condenser could contribute to the improvement of reliability and stability of the small isolated power system, integrating renewable energy. For that reason, the synchronous condenser could be considered increasing the integration of renewable energy into a small isolated power system. Possible next steps could focus on the study of optimal rated power of the synchronous condenser, optimal value of their inertia constant, most suitable location for these devices, and analysis of other disturbance conditions in the power system. And finally, just a comment, this work was carried out within ResMap project. ResMap project is funded by the European Commission, and the authors would like to thank the Renewable Energies Department of the Canary Islands Institute of Technology for its special support. And that's all. Thank you so much for your attention.
Okay, thank you very much, Elias. We have time for 1-2 questions. Could you stand up, please?
I think it's, yes, okay. Thank you for the presentation. My question is whether in your modeling you considered any inertia contribution from the renewable generation, like the wind farms. If you put like zero...
Excuse me, I don't listen very well.
Okay. Was it too loud?
Okay. Could you repeat, please?
Yes. Is if you consider any inertia contribution from the renewable generation, from the wind farms, or if it was zero in your model.
Thank you for your question. The inertia considered in the power system is provided by the conventional generation units. Renewable energies don't provide inertia response. Only the inertia in the power system is given by the conventional generation unit and the synchronous condenser in this case. Thank you. Thank you.
Okay, thank you very much indeed.
Thank you.
Okay, thank you. Let's go for the second presentation today, entitled Strategies and Limitation for the Detection of the Subsynchronous Oscillation in Power System by Stefano Lodetti, coming from the National Physical Laboratory of UK. Okay. Yes, this is the presenter. How should I
Yeah, good morning, everyone. My name is Stefano from the National Physical Laboratory. Presentation today is about the detection of subsynchronous oscillations in power systems. Subsynchronous oscillations are power system oscillations at frequencies that are less than the system frequency, so less than 50 hertz in Europe. They usually arise from interaction between equipment, and they usually are concerned in the transmission system. Traditionally, they would originate from electromechanical interaction, but more recently, we're seeing the occurrence of oscillation due to the interaction between power electronic controllers, so they're very much related to renewable generation. They're quite dangerous. If they're not damped, they can cause damage to equipment, they can cause disconnection of generation, and in worst case scenario, they can lead to a loss of supply. We're observing increasing occurrence of such oscillations, especially in systems with a high penetration of inverter-based generation, so renewables. So Australia, Northern China, Texas, Scotland, system where the system strength is going down. Here, these are some examples of oscillations detected in the last 10 years. And this is an example of how they look like. This is an example from the GB, Great Britain National Grid, of a couple of oscillations that occurred in Scotland 2 years ago, about 8 hertz. System operators are very much concerned by these oscillations, and they do have a need of having more awareness, more situational awareness, and increased real-time monitoring capabilities. Currently, the way to see this oscillation is by using instrumentation that is already deployed in the system. So that was not designed for oscillations, but it's already there. So one way is to use digital fault recorders. They can provide the very high sampling rate, so they can give you the waveform, the voltage and current waveforms, but they don't have real-time capabilities. So they're not really useful for early actions. The only viable option currently is to use phasor measurement units, PMUs. They do have real-time capabilities. They are GPS locked, but they don't provide you with the waveform. They only give you a phasor, which is something that is more or less proportional to an RMS value. This is a typical measurement chain. Here you have the grid, what you want to measure. So you would have some sort of instrument transformer, and then you have a digitization stage. So this is where the PMU is. And then another stage, which usually is inside the PMU, but it's your detection algorithms, your characterization algorithms. And then you can get some visibility of oscillations. Now, this measurement chain, when you work at 50 hertz, it's quite okay. Your instrument transformer usually is calibrated, so you can trust it. PMUs, there's a standard. They come with a stated accuracy, so you can trust the result of 50 hertz, and then there's a variety of algorithms, so all works fine at 50 hertz. When you go away from 50 hertz, you can have, despite having like very good algorithms for the detection of SSOs, of subsynchronous oscillations, there's some issues. Your instrument transformer, you don't really know how it behaves, what's the frequency response, especially if you're far away from the 50 hertz, a very low frequency or very high frequencies. PMUs, really, we don't really know how they behave at 5 hertz, 8 hertz, we don't really know. So even if you have a very, very good method, if you cannot trust the input data, there's a question on whether you can trust the output of your method. So this presentation is about this stage, about the PMUs and how they perform. PMUs have limitations. One of them is the reporting rate. There's a theorem in sampling theory that says that the maximum frequency you can see, it's half of your sampling rate, of your reporting rate. And PMUs typically, for 50 hertz system, they typically report at 50 hertz or 100 hertz. So the maximum frequency you can see is either 25 or 50 hertz. Because of this reason, PMUs carry anti-aliasing filters, so they want to remove everything that is above your maximum frequency to avoid noise. But they also carry other filters. In particular, they have narrow bandpass filters around the 50 hertz. This is because PMUs are designed to measure the 50 hertz very accurately, and to reject everything else, because everything that is not 50 hertz is considered noise, distortion, and they just affect the accuracy of the measurement. So we've done some tests to assess the performance of PMUs. We generated artificial waveforms with a 50 hertz component and an oscillation at varying frequency. And we pass it through PMU algorithms, and we obtain the phasors, the oscillating phasors. And we've done some frequency analysis on it. One of the studies that we've done is the frequency identification. We've seen that if we create an oscillation of 5 hertz, and you pass it through the PMU algorithm, then the PMU will see something at 5 hertz. So that's what you injected. But interestingly, if you inject 45 or 55, you still see 5 hertz in the frequency analysis of the phasor. That's something that's known as beating, because 45 and 55, they are 50 plus or minus 5. So in the frequency spectrum, you see 5. But effectively, the result is that if you measure with the PMU and you see 5 hertz, you don't really know if it was 5, 45, 55. We can also see that the amplitude is attenuated. So in these two cases, it's about 50% of the original amplitude. But in the case of 5 hertz, you can see the amplitude is very attenuated. So in this case, everything is pretty much ideal, so we can see it. But if we had noise, then we wouldn't be able to see anything here. A second test we've done is, we try to understand this attenuation, how it works compared to the frequency of the oscillation. So we did a frequency sweep from 1 to 65 hertz. And we tested different PMU algorithms. They're all like standard compliant, IEEE standard compliant. And you can see that if you're analyzing something around 50 hertz, then the attenuation is very little. But as soon as you move away from the 50 hertz, then you start having important attenuation. And in some cases, even very aggressive. And in general, it's worth noticing that the most accurate PMU algorithms are these ones, the ones that can really reject the out-of-band components. But this is one you want to measure when you're looking for SSOs. So you can see where the problem is. So in order to understand, to fully characterize the limitation of PMUs, the strategy that we want to use is a comparative approach. So we want to measure oscillation with a PMU in parallel with something more accurate, so something that can record a waveform. We have these units that we've developed. They are basically waveform measurement units. They can sample at very high rates. They are GPS connected. We can implement the algorithms that we want. And they can also operate as a PMU. So this device can effectively perform these two tasks in parallel. And the idea is that we can characterize an oscillation from a PMU and characterize one from a waveform recorder and then compare and see. The problem is that these sample at a very high rate, and so if we wait forever for an oscillation to occur, we would just store a lot of data that contains nothing. So what we had to do, we had to develop a detector, effectively an SSO detector, to implement on the PMU, that if it detects an SSO, then it would trigger the acquisition of the waveform. The way this detector works is it works on the frequency measured by the PMU. You can see an example here. This is an oscillation. What we do is we calculate the Rokoff, so the derivative of the frequency, and then we extract the envelope of this, the Rokoff, the rate of change of frequency. Here you can see a detail. And the algorithm is relatively simple, so we define a threshold, and if the envelope of this Rokoff surpasses the threshold and stays above the threshold for a minimum duration, then we say, okay, there's an oscillation, and then we record the waveform. So this detector depends on two parameters, the threshold and for how long it stays above it. So in order to define these parameters, we did a study. Basically, we tested it with a large number of PMU recorded events. And the objective is to minimize the false positives, so a trigger when there's no oscillation, and to minimize a false positive is, yes, a trigger when there's no oscillation, and a false negative is when there's an oscillation, but you don't trigger. So we found an ideal area here, and then we defined a threshold and a minimum duration. So we defined a threshold of 0.5 hertz per second, and at least 5 seconds. This is pretty much application dependent, if you can be more or less strict. So once we defined these parameters, we tested, we validated the detector with a variety of artificial synthetic SSOs, but also with some real SSOs. These are publicly available from the Australian operator. This is where we are. The next stage is to take the detector and deploy it in the grid. We already have some of our units on the GB system. We're probably going to start here in Scotland, where the system is weaker, because there's a lot of wind, the network is not very strong. This will allow us to fine-tune the parameters of the detector, and then basically we have to wait for an oscillation to happen so we can collect it. And then we'll be able to compare the parameters and understand if phasors are enough to characterize these oscillations, what can you extract from a phasor and what you cannot extract from a phasor. So yeah, summarizing, oscillations are a growing concern. They are strongly linked to the increasing presence of inverter-based generation, and system operators consider them a big concern. They use existing measurement infrastructure because it's what they have, but we see that they have shortfalls. So we develop a strategy to understand and hopefully overcome these limitations. We've designed a detector for oscillations to put on PMUs so they can trigger when there's an SSO. And ideally, we want to answer the question of whether it's enough to develop better algorithms or if really we need new equipment. And before concluding, I have a bonus question. We've talked about subsynchronous oscillation that's below 50 hertz, but what about supersynchronous? What about oscillations that are above 50 hertz? We don't really see much. Is it because they're not there, or because we're blind and we cannot see them? So with this, I conclude, and I'm happy to take questions.
Okay, thanks, Stefano. We have time for one question. We have time for one quick question. Okay.
An answer to the supersynchronous oscillations. So you get them easily with power electronic converters. But it means in the beginning of the power electronic converters, people were considering them as a negative resistance. So if you put voltage proportional to current, you create a kind of negative resistance. And then you have easily supersynchronous oscillations. So what people did afterwards was to synchronize on the frequency and to inject a current which is synchronous with the fundamental, but not instantaneous proportional to the voltage. So they are inherent possible, depending on what type of thing you put on them, but one tries to avoid them in power electronics.
Okay, thanks. Thanks for the comment.
Okay, any comment or questions? Okay, I think that's all. Thank you very much. Okay, next presentation by Luis Bejo is development of a prototype to maximize renewable energy for integrating applying experimental studying on DLR. It's coming from the Department of Electrical and Energy Engineering of the University of Cantabria.
Okay, thank you very much, Chairman. Luis is the corresponding author, but my name is Mario Mañana. I am one of the members of the team. Okay, this contribution is basically just a description of a setup, a facility, just to test technology related to ampacity studies or dynamic line rating. It's a very simple presentation, but I would like just to link with the importance for the integration of renewable energy, especially on decarbonized grids. Okay, the outline of the presentation will include just a small review of the context in which this setup facility can be considered, especially with the growth of the renewable energy, I will review, because maybe some of you are not familiar just with this technology, so why this is a solution to increase the capacity of electrical infrastructure. So I then will review the thermal balance and the standards, the IEEE and the ICREPQ technical brochure that defines the requirements that are needed in order just to define a setup facility like this one. And then afterward, I will just summarize the features of this platform, some results, and the conclusions. Okay, I think this is not necessary just to explain what is happening just with the generation mix, but what maybe is not well known is what is happening with the distribution networks that has to absorb a high percentage of renewable in a distributed way. So just to give you an example, in this I don't know if yes. This slide shows what is the relation between the renewable capacity and the peak demand radio. Yes, not only in several Spanish DSO, but in the case of Viesgo, the distribution network is becoming more and more just close to the transmission instead of a distribution. So the power flow is moving up instead of down in several areas. And the thing with this just reversion of the power flow is not only concerned with what is happening with the stability of the network, but also is moving the network just to the limit of the static limit, to the operating static limit. So this is something that is worrying just the operating of the networks. So in this context, this is not an isolated case, because just to give you an example, 2 weeks ago, the government of Cantabria just published a resolution declaring an environmental impact. This is a very classical resolution. So if you browse the official publishing, you will find a lot of documents like this one. But just what strikes me is that in the alternatives that are approved by the government, the alternative number one defines that, okay, we propose to maintain 15 turbines positioned with a total capacity of almost 50 megawatts, either by increasing the capacity of the existing power line or by constructing a new one. So in this case, the wind farm has been approved before increasing the capacity of the network. This is a common scenario, and is moving the DSO just to a position that is not very comfortable in terms of just managing the network. So at the end, what is happening is that the politician push just the DSO just to integrate more energy without giving the tools to increment the capacity, the necessary capacity. So what is the solution for that problems? So if we just review the available solutions, we have 3 main sets. The first one is, of course, to build new infrastructure, but you know that that is difficult. Of course, it's a good solution from the point of view of the additional capacity that has been provided to the system. But of course, if we study the KPI of the solution in terms of the design, in terms of cost, in terms of constraints, so you know that in general there is a NIMBY approach. So most society refuse just to install new infrastructure. So on the other hand, this is not a short process. So the time that is needed is too long. The second approach can be to upgrade, to repower the existing infrastructure just by increasing the voltage, or by just updating the conductor using high temperature conductor like ACSS or ACCC. This is a second option. the DSO are not comfortable with this type of technology. I don't know what is the reason, maybe because they don't have a history of using. And the last one is the dynamic light rating. Dynamic light rating is cheap in terms of the overall cost, because maybe can be considered something that is less than 2% of the cost of a new infrastructure, and in addition can be implemented in a quick way. Of course, that is not a solution for a general point of view, but in areas in which the distribution network is radial and the wind farm has to be just integrated into the grid, so more wind means more cooling, so these techniques can be suitable. Okay, so we will focus very quickly in this approach. Just for those of you who are not familiar with this technology, what is dynamic light rating? It's basically just to consider the thermal balance in a conductor in which the heat that is gained, and is gained because the Joule heat mainly, but also because the radiated sun and also magnetic and corona in a very short contribution, okay? And on the other hand, we have the heat loss, basically convection. And convection can be increased when there is a wind speed that is removing the heat from the conductor. So this is in a steady state, and if we consider the transient, the only thing we have to add is just the mass of the conductor and the specific heat capacity of the conductor. So this is the general approach. This is not new. This is something that just is as old as the history of conductors. So if we just review the state of the art, just the concept of rating is as old as 1939. So after several improvements, the dynamic light rating appears as a concept in 1962, more or less. So this is not a new concept. And nowadays, the documents that just define in a very standardized way how to do that is mainly the IEEE 738 and the SIGRE technical brochure 601. Both documents are devoted to conductor of type aluminum conductor steel reinforced. So one of the aims of this platform that we have developed is just to test other type of conductor as high temperature conductor in order to know if this standard can be extended to those type of conductor. One of the objectives of this setup facility was just to compare the standards. So if you are interested, we have some publication related to this topic. So I am not going to just to extend. And that is the facility. It's a very simple setup in which we have a loop in which we are able to test real conductors with a maximum current of 2,000 amps, of course, with a very low voltage. So because we are interested only on the Joule effect. But this platform is not only for testing a conductor. It can be used also for testing all the temperature or other technologies that are needed in order just to put to the test this technology. For instance, weather station. Here we have two integrated weather stations that are used by Viesgo and by EDP. Okay, and we have this is a conductor temperature sensor, a wireless temperature sensor that is used by Viesgo. And at the same time, we are also able to test other developments proposed by our research group. Okay, basically, and you have more details in the paper that has been submitted to the conference, we design a prototype in which our objective was just to keep as small as possible, but at the same time, just avoiding the lateral effect of the cooling system due to the auxiliary element. So in the central part of the conductor, the temperature can be considered more or less stable. So we can use this part just in order to evaluate the behavior of the overall system. Okay, this is an example of in which we test a heat sink element that can be used to extend the area, and with a wireless temperature sensor, we are able just to measure the temperature of the conductor without any element in contact with the cable. This is suitable just for application, for instance, in substation, or in application in which we are able to just to link or to connect this sensor to the IT network of the utility. Yeah? Okay, so the other part that is interesting for us is all the architecture of the system that is able just to collect and to manage the data. We have designed a system that is a data-driven system in which all the data is stored in a SQL, in a relational database. So once the data has been stored in this type of system, it is possible just to analyze, to explore the data by means of any tools you consider, like Python or MATLAB or any other. Okay, this is an example of a website application in which we are able to publish the results. And finally, because this is the work that has been carried out by a PhD student, but that is the corresponding author, and is a doctoral thesis that is going to be presented in the next month. Luis studied just the behavior of a high-temperature conductor in order to test if this conductor is suitable or if the standard can be applied in this case. Okay. So just a conclusion, the prototype has been designed with a particular focus on aluminum conductor steel reinforced, but it can be extended to other technologies with a current that can be increased up to 1,500 amps. The prototype is very easy to use. Of course, it has several limitations. The main one is related to the fact that the weather conditions are the ambient condition in the place in which the system is installed, but as the weather conditions are similar to the real condition of the BSGO, that is the DSO of our area, this is just can be not a big problem, a big issue for us. And that is mainly everything. So thank you very much for your attendance, and if you have any question, I will be happy to discuss. Thank you.
Okay, thanks a lot. We have time for 1-2 questions. I have one.
Okay.
I'm coming from a chemical engineering background, so I'm very interested in these convection losses.
Okay.
How do you really estimate? Do you use correlations? Do you take into account the speed of the wind, the density?
Yeah, well, it is something that is well known, and the standard defines how to apply analytical equation just to obtain what is the cooling provided by the wind. I forgot to mention that in our case, we are considering only horizontal wind speed. We are using weather station with ultrasonic anemometers. And that is important because when the convection is important is when the wind speed is more or less greater than 1 meter per second. If wind speed is lower than that speed, instead of forced convection, you have natural convection, and the capacity of the cable just reduce a lot. So it is important just to evaluate what is the minimum amount of wind speed, because wind speed is the most important weather condition, more than temperature, more than solar radiation. Yeah? So the key point in order to just to estimate what is the maximum current that can be just transported by the cable is wind speed, and especially when you have force conversion, that is more wind speed greater than 1 meter per second. Yeah.
So you take into account only natural convection when wind velocity is low. You don't take into account.
Yes, because once the wind speed is greater than maybe 4 or 5 meters per second, and you have to consider that as this solution is mainly devoted to areas in which you have wind farms. So when you need capacity is because you have high winds. So the important thing is what happens or where is the border, the limit in which, in terms of minimum speed at which this technology can be applied, yeah, in a suitable way. So in our case, I repeat again, as this is applied in cases in which it is necessary to integrate wind farms, so the high wind speed are available. So that is not a huge problem in that case. Yeah.
Okay, nice presentation. Thank you very much indeed.
Bye bye.
Okay, thank you very much. Okay, next presentation is about cuckoo search algorithm applied for maximum power point determination by facial PV using different PV cell models by, difficult to pronounce.
I'm the second author, so. Okay, Mr. Chairman, ladies and gentlemen, thank you very much for the introduction. As the chairman said, I'll just pronounce the names. My name is Goga Cvetkovski, and I come from the St. Cyril and Methodius University, Faculty of Electrical Engineering and Information Technologies in North Macedonia. It's actually a PhD thesis of the first author. It's my student that is working on her PhD. So I'll just go briefly through the content, and then we'll start with what the paper is about, naturally. So I'll give you a brief introduction of the idea, why we decided to do this research. Then I'll give you a short introduction on the cuckoo search algorithm, something about the bifacial PV cell models, the results from the optimization, and finally, conclusion. The increased installation of PV system in Macedonia resulted in an enormous, as everywhere in the world and in Europe, an excessive power. And then because the number of installations were going very fast, actually the PhD student is working in a company that are designing and installing PV plants in Macedonia. So they came to a situation where in certain days in the year, regarding the climate conditions, the production of the PV plants exceeds the designed value, and the inverters just switch off. And the idea was to take into account different meteorological conditions, temperature, solar irradiation. For example, when they designed the photovoltaic plants in Macedonia, they take about 1,000 watts per meter square, or a little bit above that. But they found out that in some days it can be up to 1,500 or 400 watts per meter square due to the different weather conditions, wind, clear sky, low temperature, and their power production exceeds the designed values. So we decided to to find a methodology how we can predict some of those conditions and help in the design of the PV plants before they're installed on a certain site. Of course, the emergence of bifacial photovoltaics is now also an issue in Macedonia, because they're installing more bifacial rather than single-phased PVs, and they add extra power, as we will see further on. So we decided to do an investigation in this area to see how we can predict the produced power by using different cell models, as I will explain later on. As you all know that the optimization methods started first with deterministic methods, with all their pros and cons regarding their usage. Then the stochastic methods became more useful, and they have been used in many years before for different optimization problems. So we decided to use some of those. This is the circle one is the one that is presented in this paper, but we have used different methods from different group of those natural based or inspired algorithms. So we've tried with genetic algorithm, with cuckoo search, teaching and learning, and here gravitational search, and I think another one, but I can't find it here. So different methods. Why? We started with different methods because there are some papers introducing the theorem of no free lunch theorem, which in optimization application states that there is no particular method for a particular problem. So you have to search with the methods to find which of those is most suitable for the problem you're analyzing. So that's why we try to use different methods and different cell presentations to find which will be the best match for this investigation. So what's the basis of cuckoo search algorithm? As you all know, cuckoo is a very aggressive bird. It doesn't have its own nest, so it puts its egg on somebody else's bird's nest. And this aggressive approach is used to mimic this behavior of the cuckoo birds in order to have many solutions to investigate a broader area or a number of nests. And from this aggressive approach of the cuckoo bird to find or gain the best or closest to the best solution. So, for example, as you can see here, the cuckoo bird dumps the egg in a randomly selected nest. And then the algorithm using Levy flight tries to find or selects based on the objective function value which nest has the highest value. And those nests are kept for the next iteration, where some of the nests are excluded from the search as it happens in nature when the bird, the owner of the nest, finds out that this egg is not its own egg, so leaves the nest or dumps the egg out of the nest. So this is when you just leave the solutions out of and add new ones in the population of nests. This is roughly how the algorithm works. This is the block diagram of how the method is functioning. On this slide, we have the producer's data given for the single side, if you're using one side, and what happens with the values of some of the data when we use the bifacial photovoltaic cell using the other side with a bifaciality of 10%. Now, this percent changes due to the type of the surface that you have under the PV plant. So it differs from it can go up to 20% when you have a nice white surface that is glowing a lot and reflecting the light coming from the sun. So that's the best solution. So 10% is somewhere in between. Okay, let's start now with the presentation. I will not go into detail, just to show you. In literature, those models are well known. So one is a single diode, but without any resistance so it's an ideal model of a PV cell. What is added to this classical model is that we have two current sources for the front and for the rear side of the PV cell or a PV module. And as you can see, this is defined here in the equation of the current that is going out of the PV cell. These are the equations defining how we can calculate the solar radiation from the front and the rear side, or the current coming from the front and the rear side of the PV cell, and the current going through the diode. The next one is the resistances. The series resistance is the variable that we're going to change during the optimization. The parallel one is the one that is calculated using the data defined by the series resistance. So as you can see here, yeah, you see this is the equation for the parallel resistance, where the series resistance is the one that is changed during the optimization. And the last model is, but not the last one that is used in theory. There are many more with 3 diodes and extra resistances added to this model. Here we have with 2 diodes, just introducing the imperfection of the PV cell by adding another diode to the cell model. The objective function of the optimization is the power difference between the maximum power point calculated by Cuckoo search algorithm and the maximum power point given by the producer in a catalog. And we try to minimize the difference between those two powers, where the power of the Cuckoo search is calculated by taking into account the voltage and the current that is calculated. The voltage is the variable parameter. So in this optimization, we have only 2 variables. The one is the voltage, and the other one is the series resistance. It has been first, as a big starting point, we try to calculate the value of the series resistance, and it's between, in the middle of those 2 values. That's why we use the lower and the upper value to be between 0.1 and 0.3. It depends on as I said, the characteristics of the photo PV cell, as well as the solar irradiation. The solar irradiation changes a little bit, not a lot, but a little bit, the value. So that's why we use this parameter. And this parameter is changed only in the second and the third model. The first model doesn't have this series resistance, and there only the voltage is the variable parameter of the optimization. And here are now the results of the optimization for the 3 model. The first one is the ideal single diode PV cell model. So as you can see here, only the voltage is the one that has been changed or modified. The current is calculated, the power difference is calculated, and these are the powers that are been gained from the optimization for a 1,000 watt per meter square solar irradiation. On the bottom table, we have the results for 200, 600, and 1,000. On the next slide, we have the data for the real single diode cell. And also you can see here is how the value of the objective function changes through the number of generations. We've selected 100. It can be reduced to a little bit lower, but the calculations are going pretty fast. It's a matter of few seconds. So it can be, I mean, 100 is fair enough to leave for the calculations. There is a slight change about the 80th generation in the 7th, 8th decimal point of which is not feasible, but anyway, just to leave whether something will happen later on, but 100 is fair enough for this optimization, and these are the results for the last double diode PV cell model. As you can see, the optimization results, or the power of the maximum power point, is reached very close. The difference is it's a large number of decimal points, so they're we gain almost the same result as given in the catalog. As I can say that this is not the case with other optimization methods. So this method shows pretty good results regarding, for example, genetic algorithms. So it means that the algorithm also can be a case to study later on. So to summarize, we have tried to use the cuckoo search algorithm as an optimization tool to find the maximum power point of a PV module. We have used 3 different cell model presentations, so ideal single diode, real single diode, and double diode model. All work well, although the single diode and the double diode give more precise results in comparison to the ideal diode model, of course, because we don't have these resistances taken into account. So for our future work, the candidate will try to use maybe a 3-diode model to see what results we'll get from this presentation, as well as the optimization methods that I have mentioned will also be used, and then we'll have be able to compare the results and see which model and which optimization model method is suitable for such an investigation. Thank you very much for your attention.
Thanks a lot. We have time for one quick question. Okay. I have one.
Okay, yeah.
Have you tried to change the temperature in your models? Because
yes, in this investigation it has not been changed, but it's going to be taken into account in the PhD thesis. So we have tried with the temperature, but now for different conditions, for example, to take into account winter season, spring, summer, and autumn season. So yes, it will be taken. It's not presented here, but it is taken into consideration. Yes, thank you.
I think it's important.
Yes, definitely. All these calculations are done for 25 degrees Celsius, but we'll try to do it with lower temperatures and higher temperatures, especially the conditions that were found in reality, to see how this will influence. For example, good solar radiation, even above 1,000 watts per meter square, with a lower temperature, and see what we'll gain as an output power of the PV cell.
Okay. Thank you very much indeed.
Thank you very much.
We are going for the last presentation entitled A Mile Approach for Optimizing Energy Storage in a Commercial Building by Hermano Bernardo of the Center for Power and Energy System of Porto, Portugal. Okay.
Hello, good morning. My presentation is an optimizer for the IAD operation of a storage system in a commercial building. So it's more related to the demand side. The previous presentations were more broad in the application, very interesting. Mine is focused on the inside of the building. So our goal is to develop an optimization algorithm that schedules the operation of the electrical storage system in the next day, in the day ahead. It is based on power demand forecasting and PV generation forecasting. And then we have the optimization algorithm, and the results that I will present in here today are related to the energy storage scheduling in order to minimize the operation costs. The optimization problem was formulated as a mixed integer, implemented in Python using Pyomo, and the solver that I present here, we tried another ones, are Cplex. So the problem has the inputs such as energy demand, installed power, battery capacity, electricity market prices and tariffs, and then there is the computation of the PV generation energies, energy costs, the LCOS, and the minimization of the objective function. So the objective function was this one that aims to minimize the energy-related costs to the operation of the system. And we introduced the LCOS, as I will present after, as a penalty factor in order to reduce the number of cycles of charging and discharging the system. There are several constraints to reproduce the physical and operational behavior of the system. And we considered Iberian market marginal cost of energy, the grid access tariff, and the average peak power charge, and we summed all of that. And then this is the levelized cost of storage that we use in order to reduce the number of cycles of charging and discharging of the battery. So our case study was a shopping center with an annual consumption of 7 gigawatt hour and with a PV system of 1,200 kilowatt peak with excess generation, mainly before the building opens, and the electric storage systems with 800 kilowatt hour. So we analyzed 3 scenarios, the base case, the baseline scenario with energy demand and PV generation without any kind of optimization algorithm. The second scenario was related to the energy demand and PV generation, but using the optimization algorithm without the LCOS penalization. And the last one was including the LCOS penalization in order to increase the lifespan of the battery. Here we have the graphic for our simulation using historical data, and we can see then that we only have PV excess generation during the morning in these times, and not every day. When we apply the optimization algorithm, we see that the system will charge and discharge the battery according to the prices of the grid, but there are lots of charging and discharging cycles that reduce the lifespan of the battery and leading to the replacement of the battery. So we included the LCOS, and we see that there are a lot, the charging and discharging cycles reduced significantly, and sometimes there is the energy conservation from one day to another one, and the system, the lifespan of the battery systems increased a lot. Here we have a summary of the main results. We can see that the number of cycles is increased, reduced to when we apply the penalization factor. The savings reduce slightly, but since we don't have to replace the storage systems, this is the best option to operate the system. As main conclusions, the algorithm schedules the operations of the energy storage system for the following days. There are considerable savings achieved by taking the advantage of the market electricity prices, and the implementation of the life cycle, the life cost of storage improved the performance, reducing the cycles and maintaining the significant costs and enhancing the viability. As a future work, we are now working in modeling the energy storage system degradation over time, and the implementation of the option for selling the PV excess generation when it is an advantage facing to the storage of that energy. Here I can show you the platform that we are developing for simulating this. And now we are working to put this working in a near real-time operation. This is the layout of the application that we have now. Thank you.
Okay, thanks a lot. We have time for one question, please. Okay. I have one. I think I read that you are limiting the battery state of charge limited between 20 and 80%.
Yes.
Why is this? Is this a technical limitation?
That was based on literature review in order to keep some kind of charge, some amount of charge, and not to exceeding for example, in the following day, if we need to charge a little bit because the prices are lower, we have also room to charge the battery a little bit more.
And what about the lifespan of the battery?
The lifespan of the battery increases when we make the first optimization. There is no economic viability because we have several cycles across each day, and the lifespan, I think it was almost 2 or 3 years, and then we reducing the number of cycles. The lifespan increased for I don't know the exact number, but 15 or 16 years. So it was the main advantage of this approach.
Okay, thank you very much.
Thank you.
Okay, thank you very much. I think this is the end of the session A6. I think now we are going to the closing ceremony. Thank you very much for attending to this session.
few minutes.
Alicia y Philip, Alicia y Philip vienen aquí ahora también para los...
¿Quién?
Alicia y Philip vienen ahora aquí para los postres, para verlos.
No.
No vienen.
No, lo damos nosotros. Estamos nosotros para darlos.
Pero bueno, por si querían venir aquí ya
No.
que al final...
Okay. Good morning. Chairman and members of the local organizing committee, members of the steering committee and the International Scientific Committee, chairman of the poster and oral session, ladies and gentlemen. Now we must deliver a diploma and a silver plate without recognition to the 3 best posters presented at this conference. Then, take into account the evaluation of all the chairmen of the different poster sessions and the decision of the poster advocate committee members, the 3 best posters of this conference are the following. Stability analysis of grid hybrid power plant for hydrogen production. Author Llamazares, Martín Arroyo. Bestúe, Corazza, García Gracia. Smart bioinsulating composites for thermal comfort and energy efficiency. Delgado Sánchez, Tenorio Alfonso, Navarro, Partal. Stochastic methodology for system allocation in the power distribution network. Espinoza, Crispino, Martins, Salles, Almeida, Monaro, Lorenzo, Rosa, Cebrián. Don't stay here. Then we send it. Okay. Okay, now the chairman of the local committee, Benjamin Gonzalez, can say something to you.
So thank you very much. First of all, I want to thank you to all of you for participating in this conference, to come here to our island, to our university, and share during 2.5 very intensive days a lot of knowledge and a lot of challenge for the future. In particular, I want to thank you to Manuel for selecting us as a local committee to host this conference, and also for the passion that yearly he is showing us to keep this conference alive. Also, I want to thank all the chairmen and chairwomen for their participation in this conference. And also, I want to make a particular mention to my colleagues in the local committee, Professor José Gómez, Carlos Efrén, Silvia, Javier, and Ernesto, for their passion and, well, perhaps unpaid work that they have been performed during these days. Also, I want to thank the sound techniques, Tamara and Josue, because they have been here early in the morning. They have been last in the day, doing a very good job from the company Vora. And also to perhaps a silent part of this conference, that this is a core of this conference, and they keep alive. So Alicia and Philippe, because they have been working so hard. So on behalf of us, for this reason I was asking if you are coming. Please, Alicia. And to conclude, to Professor Mañana, good luck for the next. Thank you.
It was a pleasure to be here with you in this beautiful city of La Laguna. But now I am closing the 23rd International Conference on Renewable Energy and Power Quality. I am sure that you, like myself, have enjoyed the conference, La Laguna, Tenerife, and the Canary Islands. Thank you very much to all the members of my team, especially to Alicia, Juan José, Lerly, Manuel, and Andrea, and also to Philippe, who has helped us during the conference days. Thank you very much to the local organizing committee members, especially Benjamin, José Francisco, Silvia, Javier, Ernesto. If we try to look to the future, I might say you that we are looking for a suitable venue to celebrate the 25th anniversary of the conference in 2077, but the 24th edition of the conference the next year will be held from the 10th to 12th of June in the nice city of Santander. Now the chairman of the local organizing committee, Professor Mario Mañana Cantelli, will present you Santander, the university, with some picture and video. Okay, this was a very nice picture that all things.
Okay. Thank you very much, Chairman. I would like to take this opportunity to also congratulate and thank the entire organizing committee of this nice conference, not only for the high scientific quality and inspiring of the contribution, but also for the time we shared together over these past few days. The settings, the facilities, and all the effort and dedication you have invested have made us feel fully comfortable. Now, as the chairman mentioned, it's time to look ahead to the next year, and on behalf of the Department of Electrical and Energy Engineering at the University of Cantabria, my university, north coast of Spain, so for some of you that are familiar with the place, I would like to invite you to take part in the 2026 edition. Santander is a small but vibrant city on the shores of the Cantabria Sea. So we share the ocean too. I'm sure that you will enjoy both the conference and the time you spend in our city. Since a picture is worth 1,000 words, is better than 1,000 words, I believe the following video will convey what I am trying to express. Yeah?
One time more, we would like to thank to all the authors, participants in person and online, session chairman, steering committee, international scientific committee members, postgraduate committee members, and also to the sponsor, and all the people that work and collaborate with this conference from the La Laguna University, and of course to the university, to the rector, for permit us to celebrate this conference here in the University of La Laguna. Definitely, thank you very much for to attend all of you to the International Conference on Renewable Energy and Power Quality here in La Laguna. And we hope see you in the next conference, the next year in Santander. Fortunately, now I don't have classic lecture in the University of Vigo. I am retired from the university, and I have much more time to dedicate to the organize with Mario Mañana the next conference, and I am sure that Santander is a very beautiful city. I am sure that the next one will be a very, very nice, very good conference, and we hope to see you, all of you, there in Santander. Thank you very much for all for staying here. I hope that you have a nice travel to your home, and see you next year. Okay. Okay. We have lunch.